You know, I was trying to set a timer yesterday while I was cooking. My hands are covered in flour, the pan is sizzling, and I shout at my smart speaker.
And you get to pause.
In silence. The spinning blue ring.
The spinning ring of death.
It's only, what, 2 or 3 seconds? But it feels like forever when you think the onions are about to burn. Then finally you get the little beep. Okay, timer set.
Right. It completely breaks the flow. It's not a conversation at that point. It's a transaction. You issue a command, you wait for the server, you get a result.
Exactly. It's the can you hear me now of the AI world. But the reason we're talking about this isn't just my cooking. It's because we're looking at a new framework that claims to fix this exact problem.
A framework called delayed streams modeling, or just DSM.
And the promise here is, well, it's huge. It's about bridging that gap between human conversation speed and machine processing speed.
It really is a fundamental shift. We're digging into a technical paper from researchers at QTI, and they're focused on streaming sequence-to-sequence learning. What they're proposing moves us away from that whole wait, read, then generate model.
To something that's genuinely synchronous.
Yeah.
And just to set the stage for you, we're not talking about a slightly faster voice assistant here. We're talking about a change in the architecture itself, the kind that lets a machine listen and speak almost at the same time.
Like a live interpreter. To really get why that's a big deal, you have to look at how it's done now. Think about the big models like Whisper.
Which are offline, right, or prefix-based.
Exactly. Which means the model basically says, hold on, I'm thinking. It needs to hear your entire sentence, or at least a big chunk of it, process that whole audio file.
And only then does it start generating the text.
Right. So it's like a translator who waits for you to finish, looks at their notes, and then gives you the translation.
As opposed to the interpreter who's whispering in your ear while the speaker is still talking.
Precisely. DSM processes the input and the output on the same time grid. It's streaming, not batch processing a finished file.
Okay, so let's get into the weeds. How do you build a model that does that? Because, standard LLMs, they think in a straight line, input first, then output.
That's the concatenation method, yeah. You feed in a prompt, it predicts what comes next. But DSM uses what they call a multi-stream architecture.
So not one line, but multiple lines.
Think of it like two parallel tracks running side by side.
Like a film reel, maybe? The picture and the sound running together.
That's a great way to put it.
Mm-hmm.
You have your input stream, say, the audio of your voice, and next to it, the output stream, the text. And the model is looking at both at the same time.
So it's not waiting for the audio stream to finish before it can start on the text stream.
No, and this is key. The alignment between the two happens in pre-processing. The model is trained on this pre-aligned data, so its job is just to predict the next token in the stream based on what's happening right now in the stream next to it.
I saw in the notes that this also unlocks a huge efficiency win, something called batching. Why is that so hard for streaming?
Oh, this is a massive deal for anyone trying to actually, deploy this stuff.
Mm-hmm.
Most streaming models are just awful at batching.
Why?
Because if you have 10 different people talking at different speeds, the model has to juggle 10 different states. It's chaotic, computationally.
Everyone's at a different point in their sentence.
Exactly. But with DSM, because everything is locked to that constant framework, those parallel tracks, it can process tons of sequences at once.
How many are we talking about?
Well, get this. On a single H100 GPU, they could process 400 simultaneous sequences.
400? That's
Yeah.
why 400 conversations on one chip.
Yep. It just sees it all as predict the next frame. It doesn't care if one person is saying a hull and another is midway through a monologue. The cost is stable.
That kind of throughput is what makes a feature go from a cool demo to something you can actually afford to put in an app.
It is, but there's a reason it's called delayed streams modeling.
Right, I was going to ask about that. The goal is zero delay, instant response. So why build a model around delay? It seems counterintuitive.
It does, but you have to think about causality.
Oh, okay, we're getting philosophical now.
A little. But think about it. If I start a sound like KN, am I saying night as in evening or night as in shining armor?
You have no idea until you hear the next sound or see the context.
Right. You need a little bit of future context to understand the present. If a model tries to transcribe the very instant a sound is made, it's just guessing. It's going to make errors. It needs a buffer.
So the delay in DSM is that buffer. It lets the model hear just enough of what's coming next to be confident about what it's writing right now.
Correct. The researchers frame it as a direct trade-off between latency and quality. If you shift the output stream delay it by a certain time, The model gets to see T steps ahead in the input before it has to commit to an output.
So more delay gives you higher accuracy, but it feels slower. Less delay is faster, but you risk more errors.
Exactly. But here's the part I found really brilliant. Delay conditioning.
The knob.
The knob. Before, if you wanted a model with 1 second latency, you had to train a 1 second latency model. If you wanted 500 milliseconds, you had to train a whole new one.
Which is incredibly expensive. You can't have a separate model for every use case.
Right. But DSM's speech recognition model is trained with random delays. So it learns to handle that trade-off on the fly. At inference time, the developer or even the user can just turn a dial.
So I could say, okay, I'm transcribing a medical dictation. Give me maximum accuracy. I can wait a second.
Or
I'm just chatting with friends. I want speed. I don't care about a few typos.
exactly that. You can tune the latency on the order of about 300 milliseconds without ever changing the model. It puts the control in your hands.
That is unbelievably flexible. Okay, so we have these parallel streams, but there's a translation problem. Text is made of tokens. Words, letters. Audio is a continuous wave. How do you get those to run on the same track?
You need a bridge. And in this paper, the bridge is a neural audio codec called MIMI.
MIMI.
Okay, the workhorse here. Transformers, the architecture behind DSM, they love discrete tokens. They really do not like continuous waveforms. So MIMI takes the raw audio, which is sampled at 24 kilohertz, and it basically squishes it down into a compact representation at about 12.5 hertz.
It's chopping the audio up into little digestible pieces.
In a way, yeah. It uses a technique called residual vector quantization, or RVQ. Think of it like painting in layers. The first layer gives you a very coarse, rough shape of the sound.
Okay.
Then the next layer adds detail, the next adds more refinement. So MIMI turns that smooth audio wave into a stack of discrete numbers tokens that represent the sound. And to the DSM model, these audio tokens look mathematically identical to text tokens.
So the model doesn't care if it's processing the words "the cat sat on the mat" or the sound of someone saying it. It just sees tokens on parallel tracks.
And that abstraction is what leads to the most elegant part of the whole system.
The symmetry. This was the real aha moment for me when I was reading through this.
It's beautiful.
Yeah.
Because the streams are parallel and the tokens are unified, the only difference between speech to text and text to speech is which stream you delay.
So let me get this straight. If I delay the text stream, the model listens to the audio, waits a beat, and writes the text. That's speech recognition, ASR.
Yep. And if you delay the audio stream relative to the text, the model reads the text, waits a beat to figure out the right intonation, and then generates the audio.
And that's TTS, text to speech.
One model, two direct.
That is so cool. And it gets state-of-the-art results in both, which is rare. Usually ASR and TTS models are completely different beasts.
Totally different architectures normally.
Let's double-click on that TTS side for a second, because the paper says that's actually the harder problem. Why?
Well, it's about information density. With speech to text, the audio itself dictates the timing. The speaker sets the pace. But with text to speech, you're starting with this very short, static input text and generating a much longer, time-based output audio.
Right. The word hello is 5 letters, but I could say it in half a second, or I could draw it out for 2 seconds. Hello.
Exactly. The input doesn't line up with the output's time grid. So how does the model know when to say the next word?
Yeah.
They came up with this really clever thing called the action stream.
An action stream?
Yeah, it's like a little conductor. It's an extra parallel stream, and its job is to predict actions. The main one is a special word token. When the model outputs that token, it's basically saying, okay, I'm ready, feed me the next word from the text.
So the model itself is controlling the pace. It's asking for its lines.
Yes, it syncs up the text consumption with the audio generation.
Yeah.
But there's another problem. If you see a sentence that ends with a question mark, you need to know that before you say the first word.
Of course, you're going to the store versus you're going to the store. Totally different melody.
But a streaming model hasn't seen the end of the sentence yet. So they use another stream called a look-ahead stream.
Another peek into the future.
Exactly. Yeah. While it's saying the current word, it's getting a little feed of the words coming up next. It's just like a news anchor reading a teleprompter. Their eyes are always a few words ahead of their mouth.
That makes total sense. And it can clone voices, too. The paper mentions speaker conditioning.
It can. A 10-second audio clip is enough. And what's really impressive is how it handles dialogue. It uses main and other speaker tokens, so the model learns the rhythm of a conversation, when to pause, when someone might interrupt.
Which is what stops it from sounding like two robots reading from separate scripts. It starts to sound like an actual interaction.
Captures the rhythm, yep.
Okay, we geeked out enough on the architecture. Let's talk brass tacks. Does it actually work? What do the numbers say?
The numbers are very, very strong. For ASR, for the speech recognition, they got a word error rate, or WER, of 6.4%.
And how good is that?
That's excellent. It beats other streaming models, but more importantly, it's right there with the top-tier offline models. Whisper is around 6.1%.
So you're getting all the speed of streaming without the usual accuracy penalty.
Pretty much. And for TTS, the latency is incredibly low. They can generate the audio in as little as 150 to 400 milliseconds.
Which is right in the ballpark of human response time in a conversation.
It's fast enough to interrupt you.
Wow.
But again, for me, it comes back to the throughput. We mentioned the 400 sequences.
Right. How does that stack up against, say, trying to make Whisper do this?
It's not even a fair fight. If you try to hack Whisper into streaming, you have to keep refeeding it partial audio.
Yeah.
It's incredibly inefficient. The paper says it's about 100 times slower in throughput.
100 times.
Yes, because DSM was built for this. It's just efficiently chugging along, frame by frame.
That's what makes it commercially viable. You can't run a service that needs a GPU for every single user. And it can handle long-form stuff, right? Like
Like
meetings.
infinite input. A 4-hour meeting, a live broadcast, doesn't matter. An offline model would try to load that whole thing into memory and just crash. DSM just keeps flowing.
They built a demo app with this, didn't they? Unmute.
Yeah, unmute. It's a voice chat interface. They wired up DSM ASR, DSM TTS, and a language model. The result is a voice assistant with sub-second latency. It doesn't feel like you're talking to a computer that's buffering. It just feels like you're talking.
That's the holy grail, the Star Trek computer.
Or the OS from the movie Her.
Hopefully with a happier ending.
Let's hope.
So to recap, we have a synchronous parallel architecture. It solves the latency versus quality problem with a controllable delay. It uses a codec to make audio look like text. And it is insanely efficient. It really sounds like a slam dunk.
It's a huge breakthrough. It shows that decoder-only transformers can handle this kind of continuous multimodal data if you just set them up the right way.
But I'm sensing a but. There's always a but.
Well, not about the text performance. It's more about the implications. There was a little section at the end of the paper on security that really jumped out at me.
Yes. The watermarking.
Exactly. We're all worried about deepfakes, right? And the main solution people are proposing is audio watermarking, embedding an invisible signal that says, this was made by AI.
A digital fingerprint.
Right. You have open source tools for this, like Audio Seal. But the researchers found something, well, something disturbing. When you take audio that has one of these watermarks and you run it through the Mimi codec,
The bridge that makes this whole thing possible.
the watermark is almost completely erased.
Wait, what? The compression process just scrubs the fingerprint clean?
It scrubs it. Mimi is so good at compressing the audio down to its essential components that it sees the watermark as just noise, as an inefficiency, and it gets rid of it.
So the very technology that enables real-time, human-like AI conversation could also be the thing that makes it impossible to detect.
It poses a massive question. If the compression you need for speed breaks the security you need for trust, where does that leave us? We might be creating a world of perfectly fluent, perfectly convincing AI voices that are also perfectly untraceable.
That's a heavy thought to end on. We're running as fast as we can towards seamless conversation, but we might be leaving the safety tools behind.
It's the classic innovator's dilemma. Better, faster.
Yeah.
But with brand new risks.
Well, the next time your voice assistant answers you instantly, you'll know about the invisible machinery and the invisible delays that make it possible. And maybe you'll wonder if it's got a fingerprint.
Indeed.
Thanks for listening to this deep dive. We'll catch you on the next stream.